In this segment we're going to analyse the mass falling from a pulley from a slightly different perspective than our previous video. So we start with the same setup, and this is the setup that you might see in an elevator, for example, in a shopping centre or a building. We have a large heavy pulley of radius r, mass big M, and suspended from it on a long light meaning that we don't care about its mass, cable or wire is a smaller mass, small m. In fact, we're going to do our solution in such a way that it doesn't really matter which mass is bigger or smaller, and our solution will tell us something interesting, hopefully, about how the ratio of these two masses and the radius of the pulley affect the behavior of the system. So we would like to find, what is our aim? Our aim is to find the acceleration of the falling mass. That is our goal. So assumed in this is that the mass only falls at a rate such that the pulley rotates with it. And that will be true as long as the mass is constantly accelerating. And as we will see, that turns out to be the case. So where to begin? Okay, we're going to begin by looking at the mass itself and the forces that are acting on it and using Newton's laws. So we know that there's a force downwards, which is mg, and we know that there is a force pulling up on this mass, and that's just the tension in this string, whatever that tension might be. Now we know that in general, the tension and the weight of the object will not be the same. If the object is falling, then that presumes that the weight of the object is bigger than the tension, and so there's an unbalanced force. What does Newton's laws tell us about unbalanced forces? Is that when there's an unbalanced force, there will be a changing velocity. That's Newton's first law. Newton's second law tells us how big that changing velocity will be, or in other words, what the acceleration will be. So let's use that. So Newton's second law says that F net, the net force in any particular direction, which in this case is the y-axis, will be equal to ma, where m is the acceleration of the body. So can we find A? That's the A that we're trying to find here. Well, luckily we know F net because we know that mg is the only force pulling down and that T is the only force pulling up. So mg minus T must be equal to ma. Now, what is the mass pulling against as it falls? In other words, what's the origin of the tension? So let's look at the system. Well, everywhere in a rope that is under tension, the tension is the same. That's one of the definitions of how tension works in a rope. So that tells us that up here, the very same T is pulling down on this mass, this pulley, and it will act to cause a torque to be exerted on the pulley, where the lever arm is equal to the radius here, because there's the radius, and that forms a 90-degree angle with the force. So this radius multiplied by this torque will equal, this force will equal the torque exerted on the pulley. So the torque exerted, tau, is going to be equal to R times T. Now it's also true that the torque is I times alpha. So I tend to look at this as the torque exerted and the torque experienced by the rotating object. So that's the moment of inertia, which depends on what the shape is, and this is the angular acceleration. So we know that let's see if we know here. We know that the moment of inertia of a solid flat disk or cylinder equals 1/2 mr squared. And furthermore, we know that from the definition of angular acceleration, that linear acceleration of a point on a circle moving at a certain angular acceleration will be equal to r times alpha. So we can substitute these two things into our equations. We can combine these two definitions of torque so that we have RT equal I alpha. And then having done that, we can substitute in for I and alpha. So let's do that. So we have RT equals I, which is 1/2 mRA over R. And now we can clear up and see what we're left with. So we've got T equal 1/2 m r squared a over r squared. So curiously, the radius of the pulley actually cancels out and doesn't play any further role in the solution. And now we can take our expression here for the tension and substitute it into our expression up here for the acceleration. So let's do that. I'll just bring that up the page over here. So let's call that equation 1 that we derived before, and let's call this expression for the tension equation 2. And now we'll combine equations 1 and 2 so that we have mg minus 1/2 big M A equals ma. Now we can tidy up and make little a, the acceleration, into the subject of the formula. So before we do that, I think we'll just divide through by little m in order to remove the m terms and just leave it in the terms of the ratio. So we've got g minus m over 2m a equal a. And now we can put everything together. So now we've got, let's see over here, a plus m a over 2m equals g. We take our a as a common factor. 1 plus m over 2m. Therefore a equals g divided by 1 plus m over 2m. So this is our final expression for the acceleration of the system. And if you think back to the question that we solved using the conservation of energy, you might want to go back and see if those two answers are consistent with one another or not.